Okay, 3.4, simple rational functions, and we're talking about the derivatives of rational functions then, which we've already done quite a bit, and now we're just talking about them using a little bit different language and seeing what happens as the value of x approaches the place where there is a vertical asymptote. This is just two quick examples of what rational functions look like or could be used for. This one relates velocity in kilometers per hour required to travel 100 kilometers to time. So it relates velocity to time taken to drive 100 kilometers. This one relates the temperature to the distance that you are away from the sun. So two rational expressions, rational equations, just to give us some context. What is interesting or unique about rational functions is that they often have a vertical asymptote. So there's a real simple one with a vertical asymptote at x equals 0. And what we're going to do today is talk about what happens as x approaches 0 from the left or as x approaches 0 from the right. And we're going to talk about it in terms of limits or derivatives and look for changes of sign in the second derivative and concavity and those kinds of things. Good. Right into example 1 then. Example 1 says consider the function f of x, which equals 1 over x plus 2 x minus 3. And the first thing that we're going to do is determine vertical asymptotes. Vertical asymptotes. Do you remember where they come from?
They're where the denominator approaches 0.
Yeah, where the denominator equals 0, right? That would make this function undefined, which means there's a vertical asymptote wherever the denominator equals 0. It's already factored for us. So all we need to do is, maybe I'll make a little note, this is where the denominator equals 0. So either x plus 2 equals 0 or x minus 3 equals 0. Those will both be vertical asymptotes here. So subtract 2 from both sides. X equals negative 2 is a vertical asymptote, and x equals positive 3 is a vertical asymptote. In part B of example 1, we're going to find the one-sided limits in the vicinity of the vertical asymptotes. So one-sided limits near vertical asymptotes. Now the value of the function doesn't exist at these asymptotes, but the limit does. First we're going to consider the limit from the left, then we're going to consider the limit from the right. So we're going to look at the vertical asymptote at x equals 3 first. So at x equals 3. And we're going to look at what happens as x is very close to the limit. So we're going to consider what happens to the function when x approaches the limit from the left. That's what we're talking about when you have a one-sided limit. So here we go. We're going to talk about the limit as x approaches 3 from the left, the limit of f of x. And this would then be the limit as x approaches 3 from the left of our rational equation. 1 over x plus 2, x plus 3. Sorry, x minus 3 in that second bracket. Okay, in order to do this, basically we're going to see x is approaching 3. So it's getting really close to 3. So what happens here when we sub in a number that's getting infinitely closer to 3, is that this first bracket basically just becomes 3 plus 2, okay? It's approaching 3, and then that means this bracket is approaching 5, right? But here, as x approaches 3 from the left, so it's 1, 1.5, 1.95, 1.99, and maybe we could say a little note there. X approaches 3 from the left, and then kind of just this is just the thinking of it. You're at kind of 1.5, then maybe 1.9, then 1.99, then 1.999. Sorry, I should be at 2.5 and 2.5, 2.9, 2.99, 2.999. You're getting infinitely closer to 3, but you're never actually getting to 3. So what happens to this number, this bracket? Well, it's going to get smaller and smaller and smaller and smaller as x gets closer to 3. But we also know that the sign, because x is always going to be less than 3, it's approaching 3, but it's never going to get there from the left, that this bracket is always going to be negative. So it's a very small negative number. Very small negative value. Or negative numbers, easier. Very small negative number. Okay, so now we need to think about what happens when we have a rational expression with 1 in the denominator, in the numerator, sorry, and the denominator is going to be 5 times an infinitely small negative number. That means the whole denominator is just getting infinitely small, and it's going to be negative. Well, what happens if your denominator gets smaller and smaller and smaller and smaller and smaller and smaller and smaller, closer and closer and closer to 0? What's happening to the value of the whole fraction?
Approaches negative infinity.
Yeah, it's getting bigger, except it's negative, okay? So the limit then, as x approaches 3 from the left, is negative infinity. A very large negative number. We'll write that as a sentence. As x approaches 3 from the left, f of x approaches a very large negative number. Okay, let's take a look at it from the right. And I'm going to run out of space eventually. I may as well just clear now. So this time we're taking the limit as x approaches, limit of f of x, as x approaches 3 from the right. That then is the limit as x approaches 3 from the right of our rational expression. And this time when we do it, we sub in 3, or a number infinitely close to 3. We end up with 1 in the numerator. We end up with 5 in the first bracket, 3 plus 2. And in the second bracket, we get a number that is infinitely close to 3, but approaching it from the right. So it's positive, it's greater than 3, approaching 3. So we're going to get an infinitely small number, but it's going to be positive. Very small positive number. So this bracket becomes a very small positive number. And again, if you need help with that thinking on the outside, as x approaches 3 from the right, we're thinking about numbers like 3.5, then 3.1, and 3.01, and 3.001. It's always going to be bigger than 3, so this is going to be positive, but it is getting smaller and smaller. And as the denominator gets smaller, the value of the fraction gets bigger, and it's always going to be positive because there are only positive factors. So the limit as x approaches 3 from the right then is infinity. As x approaches 3 from the right, f of x approaches a very large positive number. As x approaches 3 from the right, f of x approaches a very large positive number. Okay, so just to think about this and to graph this asymptote, I'm actually not going to do the second half of this problem. I'm not going to do it with our second asymptote. We're just going to look at what happens to this function at x equals 3. Oops. And that is, as x approaches 3 from the left, we said that we're heading down to negative infinity. So then that tail looks like this. And as x approaches 3 from the right, we decided that we were heading to a very large positive number, positive infinity. So this tells us the behavior at the asymptote at x equals 3. If we did the same thing for the asymptote at x equals negative 2, over here, negative 2, we would end up finding out that as we approach negative 2 from the right, we'd be heading down to a infinite negative value. And as we approach negative 2 from the left, we'd be getting a very large positive value. And so this rational function looks like that. That's something you could have done in functions using finding different values within those intervals. And now we're going to be able to do it maybe a step or two quicker using derivatives, which we'll bring into our next example. Okay, in example 2, we are given the function f of x equals 1 over x squared plus 1. We're going to find the intervals over which it is increasing and decreasing, find any points of inflection, and then talk about the graph and sketch it. One thing we want to notice before we move on, what do you notice about the denominator?
Has a square in it.
Has a square in it, and a square plus 1. The square of anything is always positive, and then you're adding 1. So two things. Number one, this is always going to be positive. And number two, it can never equal 0. So what does that tell us?
What if it's 0 squared?
Then you'd have 0 plus 1.
Oh, that's what you meant.
Yeah, so the denominator itself cannot equal 0. What does that tell us? No what? No restrictions. No restrictions, because asymptotes, vertical asymptotes exist where the denominator equals 0. So on our original function, we're going to talk about this at the end of the example, but just to keep in mind, on our original function, the denominator cannot be 0. So there are no restrictions to the domain. Okay, first thing we're going to do is find intervals of increase, decrease. Intervals of increasing and decreasing. Well, it's increasing when the first derivative is positive and decreasing if the first derivative is negative. So what we're going to do here is take our derivative. First, I'm going to express it with a negative power. So we've got f of x. F of x is, it's going to be 1 times, which I don't really need, x squared plus 1 to the power of negative 1. And so I'm actually going to just erase that 1 out in front, because anything times 1 is just itself. And now we're going to take the derivative of this. The first derivative, we're going to use the chain rule. So we're doing the derivative of the outer with respect to the inner times the derivative of the inner. And we could put that back into fraction form with positive exponents. So we've got negative 2x in the numerator, and our denominator is x squared plus 1 bracketed to the power of 2. Now, in this case, again, the denominator cannot be 0, and it's always going to be positive. How do we know that? Because of this positive exponent out here, okay? In this case, I'm just going to make a little note. In this case, the denominator is always positive. Why is that helpful to know? That means, so, the numerator will determine the sign. So we said we were looking for intervals of increase and decrease, which are determined by the sign of the first derivative. Well, now we know even though there's a variable in the denominator, this is always going to be positive, so the sign is going to be dependent on the value of x in the numerator. So what we need to do then is find the values of x where f of x, where the numerator is going to be equal to 0. So we're going to find values where f prime of x equals 0. These come from the numerator. And again, that's only because our denominator is always going to be positive. That means f prime of x equals 0, where negative 2x equals 0. So f prime of x equals 0, where x equals 0. So basically we're saying which values of x are going to cause this statement to be true, and x equals 0 makes that statement true. Or you could do it algebraically, you could divide both sides by negative 2, and you'd get x equals 0. So what does that mean? That means that our domain is split into two portions. It's split into values less than x, less than 0, and values greater than 0. I'm just going to write that. Now our domain is split into x is less than 0 and x greater than 0. So what we're trying to do is still find intervals of increase and decrease. We're working with the first derivative. And so in each of these intervals, we just need to find out the sign. So we're just going to make a quick table of values. We have x is less than 0, x equals 0, and x is greater than 0. We've got a test value. We have a sign of f prime of x. And then we're going to be able to tell what the original function is doing over that interval as far as increasing or decreasing. So test value to the left of 0 could just be negative 1. Test value here is just 0. But we know that this, anyway, we'll get to it. It is one of our zeros, so this one is 0 as well. And x is greater than 0. Test value could be 1. And all we're doing is figuring out the sign of the whole function, which is really just, we only have to look at the numerator, we said in this case. So I'm going to look at the numerator. I'm going to put negative 1 in here. Negative 1 times negative 2 is positive 2. Okay, so the sign here is positive. What does that tell us? That tells us that the function is increasing over that interval. If we put 1 in the numerator, we get negative 2 times 1, which is negative 2, which is negative, which tells us we're decreasing. Well, our 0 of the first derivative was 0. So what happens when we put 0 in there? We get 0, which refers to, again, the slope of the original, which means the slope is constant at that point. Or sorry, the slope is 0 at that point, not the slope is constant. Make sense? That's the work with the first derivative. In this case, we just had to be looking at the numerator. Again, if you're in this table of values and you don't have this case where the denominator is always positive, you would just have to put your test value in both places and actually do the algebra to figure it out. But here we would get -1 squared is 1 plus 2 is 4. Okay, so it'd be a positive value. And that's all we're interested in is the sign. Okay, B says find points of inflection. Find points of inflection. Okay, we know points of inflection come from places where the second derivative equals 0. And then if there's a change of sign at that point, then we know that there is a point of inflection there. So first I'm going to write down our first derivative again. And I'm going to write it all in the numerator, so with a negative exponent. So we're looking at -2x times x squared plus 1 to the power of -2. We find our second derivative. I'm going to write all the steps. It's maybe been a while since we've done this, so I'm using product rule and chain rule together. First thing we're going to do is take the second function unchanged, x squared plus 1 to the power of -2. We're going to multiply it by the derivative of the first function, dx by dy of -2x. Then we're going to add the product of the first function unchanged times the derivative of the second function, x squared plus 1 to the power of -2. So let's work that out. Here, the derivative of this function is -2. I'm going to put that back out in front. -2 times x squared plus 1 to the power of -2. Then over here we have -2x times, and this is going to be chain rule, the derivative of the outer with respect to the inner. Make sure you don't lose the exponent there or bump the exponent the wrong direction. It has to go down 1. And then times the derivative of the inner, which is just 2x. I'm going to simplify the second term here. So the first one stays the same, -2, and then in brackets x squared plus 1 to the power of -2. But in our second term here, I have a -2x, I have a -2, and a positive 2x. I'm going to multiply all those together to get 2 times 2 times 2 is 8. It's positive because there are 2 negative factors, and there are 2 factors of x. And then we've got x squared plus 1 to the power of -3. Now I'm at that point where I can pull out a common factor. The common factor, I'm going to leave the numerical factors in there. I'm just going to pull out the ugly binomial common factor, which is x squared plus 1 to the power of -3, which leaves from this first term -2 times x squared plus 1. And in the second term, it just leaves the factors 8x squared. And now rewriting that and simplifying inside this bracket. I'm going to do it in all in one step. So I'm going to write my dividing line. I'm going to put my negative exponent in the denominator, express it as a positive exponent. That's x squared plus 1 to the power of 3. And then inside my numerator, we have -2x squareds and positive 8x squared. So we're going to make that 6x squared. And then we have -2. That is our simplified second derivative. So now what's the point? Well, the value of f double prime of x is going to be 0 when the numerator is 0. So f double prime of x equals 0 when the numerator is 0. So all I need to do is take 6x squared minus 2, set it equal to 0. I'm going to add 2 to both sides. I'll do each step. 6x squared equals 2. Divide by 6. X squared equals 1/3. Square root both sides. X equals plus or minus the square root of 1/3. So these are now the zeros of the second derivative. And we need to find out if there is actually a sign change here. If there is a sign change, then we have a 2 actually points of inflection if there are sign changes here. So does the graph of the second derivative change from positive to negative or negative to positive at these zeros? Just to give us a bit of context, I'm just going to draw a number line. So basically what we're saying is that we have this value here at negative radical 1/3, and we have a 0 here at positive square root of 1/3. And I want to see if there's a sign change. So I'm actually going to choose a value down here to deal with, which is -1. That will tell me the sign of this interval. I'm going to choose 0 to determine the sign in between the two zeros. And I'm going to choose +1 to determine the sign over here. And if there's a change, then I know that they are a point of inflection. There has to be a change at both places. So from here, I'm getting f double prime of -1. Basically means I sub -1 in there. And I just have to sub it into the numerator in order to get the sign. Because this denominator, again, is going to always be positive because this x squared right here. Okay, so that's always going to be positive. So I'm just putting it in the numerator. I get x squared 6 times 1 minus 2, that's positive. Take the value of the second derivative at our next test point, which is 0. I put 0 in the top. I get -2, so that's negative. So there is a sign change over x equals negative radical 3. What about the value of the second derivative at 1? I sub 1 into the numerator here. I get 6 minus 2, which is 4. That's positive. So there is a sign change here as well. So, comma, there are points of inflection at x equals negative radical 1/3 and x equals positive radical 1/3. So far we have found where it is increasing and decreasing, and we've also found that there is a point of inflection at these two roots of the second derivative. So in part C, we use what we know to explain why the graph never crosses the x-axis. And why there are no vertical asymptotes. We already discussed why there are no vertical asymptotes, because the denominator of our original function can never equal 0. So there's no restriction on the domain. We also talked about, so back to this original function, the numerator is always positive and the numerator is constant, and the denominator is positive for all values of x. So that means that the value of this whole thing is always going to be positive over positive, which is positive, okay? So f of x is always positive because numerator and denominator are always positive. F of x cannot be 0 because numerator is a positive constant. What else? We also know f of x should say the denominator. Well, let's do this. No. The denominator here has a minimum value of 1. Can you see that? If you put in 0 here, that's the smallest you can make the denominator, which gives the denominator a minimum value of 1, which actually gives the whole function a maximum value of 1 over 1. Why is that? Well, if the minimum value is 1, all the denominator can do then is grow, which means the value of the function would shrink. Okay? Since x squared plus 1 has a minimum value of 1, comma, f of x has a max value of 1 over 1, which equals 1. And where does that happen? That happens at x equals 0. So what do we know? We know that at x equals 0, the maximum value of this thing is 1. And we know that there is a point of inflection at plus or minus the square root of 1/3. So what happens here is this thing, maybe I'll do it in a different color, or we can think about it this way. What also happens, two other things, as x approaches negative infinity, so as x gets bigger and bigger and bigger and bigger, negative, your denominator gets bigger and bigger and bigger, which means that the value of the function gets smaller and smaller and smaller. So as we are going along, this thing is going to get closer and closer and closer to 0 with never touching. Same thing is true as we put in bigger values of x, bigger and bigger values of x all the way to positive infinity. The denominator gets bigger and bigger and bigger, which means the value of the function gets smaller and smaller and smaller and smaller. Okay? So now what's happening here? We said there is no restriction on the domain, which means that this thing is actually going to come up and bend down again. Which means that there is a point of inflection, maybe it's here and here-ish, at negative radical 1/3 and at positive radical 1/3. Point of inflection means it goes from being concave up to being concave down. The tangent lines are all below the curve here, then above the curve here, then below the curve here again. And if we took our first derivative, we find out that the slope of the function is 0 at x equals 1. And we've pretty much talked about everything that we could with regard to this graph. So again, it's a rational function with no restrictions, but there is still a change of slope from positive to negative because of those points of inflections which we found from our second derivatives. Example 3 deals with concavity of rational functions. So when you hear concavity, it's either concave up or concave down, or there's a change, or it's the same over the whole thing, but either way you're looking for the second derivative then. So the function that they give us, f of x, is, in the numerator, -1, The denominator is x plus 2. So we're going to search for intervals of concavity and then sketch. Intervals of concavity, sketch. That's our goal. First step, rewrite f of x with a negative exponent. Second step, take first derivative, and then we're going to take the second derivative also. So first derivative is the derivative of the first times the second. Well, the derivative of the first is 0, so we can ignore that completely, and we can skip to doing the first times the derivative of the second, which is chain rule, derivative of the outer with respect to the inner times the derivative of the inner. We can simplify this. This is just 1, and we're not going to put it with a positive exponent in the denominator because we actually need to take the derivative of it. So -1 times -1 is +1 times 1 is +1. Anything times 1 is itself. So we just have x squared, x plus 2 to the power of -2. Second derivative, taking the derivative of the derivative. -2, x plus 3, x plus 2 to the power of -3 times the derivative of the inner, which is 1. And then this, when we reduce it, we can put it back in rational form. So we've got -2 in the numerator and x plus 2 bracketed to the power of 3 in the denominator. A couple things to note here. The numerator is a constant. Numerator is constant. F of x, so f double prime of x can't be 0. It will never be 0. We also need to note that there is a vertical asymptote. If we look back at f of x has no vertical, does have a vertical asymptote, has vertical asymptote at x equals -2. And the denominator changes sign at that point. It has a vertical asymptote. Denominator changes sign here at x equals -2. So f double prime of x also changes sign. Why is that necessarily true? Remember, the second derivative talks about being concave up or concave down. We have a maybe actually, because we're sketching it anyway, maybe I'll just make that drawing bigger. You can sketch yours wherever. So we have an asymptote at x equals -2. It's a rational function. To the right of x equals -2, the value of the function is positive. To the right of x equals -2, the denominator is positive. So the value of the function is negative because our numerator is a negative constant, which means that this leg is out here. And to the left of -2, the denominator is negative. and the, what am I doing here? I'm talking backwards. I'm to the left. I just drew the leg to the left of -2. Now I'm talking about to the left of -2, where the denominator will be negative and the numerator is negative, so the value of the function is positive. Over here, to the right of -2, the denominator is positive, and the numerator is negative, so the whole function is negative. A negative over a positive. So this leg looks like that. Now to get back to what I was actually talking about. F double prime of x also changes sign necessarily. If you have a leg that is going from 0 and turning up to positive infinity, this is concave up, right? Your tangents are all below the curve. On the other side of that asymptote, you will naturally have the place where you're going from negative infinity and approaching 0, which is concave down. So that is why the second derivative will necessarily change its sign in a rational function where there is an asymptote. And we can say the same thing by using a little table quickly, like we've done in the other ones. If we have intervals, we have to the left of -2, we have x equals -2, and we have x to the right of -2. And we can take a test value, let's say x equals -3, and to the right, we could say x equals -1, or you could even make it easier and take x equals 0. And then just finding out the sign of the second derivative at that test value. Well, the sign of the second derivative, when x is -3, you'd have negative value here, cubed, which would still be negative, which would be a negative over a negative, which is a positive, which is exactly what we said, that to the left, we would see concave up. If we take our 0, the slope there is undefined. Sorry, the second derivative is undefined. Undefined. And that's because there's a vertical asymptote. You can't talk about the slope at that point. Maybe for here we should say that this is concave up. That's the conclusion. Concave up over this interval. And then over here, if we sub in 0, we get a negative over a positive, which is negative, which means we're looking at concave down for the leg to the right of our vertical asymptote. So again, we're just, we sketched some functions talking about the slope and asymptotes in terms of the derivatives and second derivatives and the zeros of the second derivative in order to get our intervals, test values, talk about what's happening. Is there a change of sign at each point of inflection? If there are a point of inflection, this one didn't have a point of inflection. This one had an asymptote. But then you can talk about concave up, concave down, and sketch your graphs. Practice problems come from page 183, and you should be able to do 1 through 8.